In discussing simple harmonic oscillation or simple harmonic motion, I'll remind you that there's criteria for it. Harmonic motion is anything that repeats itself while moving, but simple harmonic motion means it can be modeled using a sine function or a cosine function. What we found is that in a generic sense, if you have a system that has an unbalanced force and you apply Newton's laws, and that can be either Newton's laws for torque or Newton's laws for force, and you solve for the acceleration, and you get an acceleration equals a minus sign times a constant times a displacement. That's a harmonic oscillator. If the acceleration equals a minus sign times the constant times displacement. Not just a harmonic oscillator, that is a simple harmonic oscillator. So if you solve this by using Newton's laws and set it equal to ma, and you solve for a, and you get something that looks like this, then you know it's a simple harmonic oscillator, and you know omega equals the square root of the constant. We've done this twice now. For the spring mass, we found omega is equal to the square root of k over m. For the pendulum, we found that the value for omega is equal to g over L, square root of g over L. Anything that appears to be a simple harmonic oscillator has to have an acceleration that looks like this. We know that there is a set of motion equations that have period and frequency and location and velocity and acceleration. They all have this term omega in it someplace. So if you can find out what causes your object to, or if you can study the way an object moves, you should be able to determine what causes it to oscillate. Now, yesterday we did this for the pendulum, and then we did a quick experiment to show that it was true. Well, we're going to try that again today for one of our last specific oscillators, because there's a group of them we're supposed to know. Definitely supposed to know the spring mass, definitely supposed to know the simple pendulum. Today we're going to talk about the physical pendulum. The physical pendulum. Most pendulums are physical pendulums. And what that means is you can grab any object you want. If you hold it by a corner, if you hold it by something that's not the center of mass, it is likely able to oscillate back and forth. Right? Just about anything you have can be made to be a pendulum. We call this a physical pendulum because a simple pendulum concentrates all of its weight at the very end, and there's nothing with mass connecting it to the pivot point. But a physical pendulum, it's not like that. A physical pendulum has extension, so it's going to be a little bit different than a simple pendulum. It's not ideal. It's the real thing. So I try to draw a bowling pin. A spoon? What kind of spoon are you eating with?
I like one of those like spoons, like a salad spoon, I guess.
Or like you place like a ladle.
A ladle? Like a spoon rest?
Yeah.
Okay.
Sure.
Sure. Okay. So we'll go with some random shape. Things, because unlike our last one where all the mass is concentrated at the end, this object's going to have a center of mass somewhere. So we're going to say this X marks the center of mass. And if we hold it at the center of mass, it's not going to oscillate. Because if we hold it at the center of mass, the mass is uniform all around it. So we're gonna mount it, say, right here, and make this the pivot point. So a physical pendulum is going to have a center of mass. So we'll say center of mass. And it's going to have a moment of inertia. Now, yesterday, when we did the pendulum, we did it two different ways. Do you remember? Once using forces and once using torque. Which one was easier? Yeah, how about we use torque for this one? I think it'll be easier, okay? So we're going to use the concept of torque here because I think it'll work out better for us. And I'm going to go ahead and put this line here to represent like equilibrium. And I'm also going to draw this line that represents the distance to the center of mass. We're going to need that because, remember, the gravity acts at the center of mass. So I'm going to need to know the distance from the pivot point to the center of mass. That's how we're going to achieve torque on our object. So this is x, center of mass. Okay, remember the goal here is to see if we can get an acceleration equals a minus sign times a constant times a displacement. So I'm going to start with net torque equals I alpha. That's where I'm going to start. The right side is just going to stay I alpha because this is a weird shaped object. I don't have an I that's sitting on the chart that I could use. So I'm just going to leave it as I. But the left side, I need to calculate the torque. And if you remember, there are three things that constitute a torque. R times F times the sine of an angle. So what is causing a force on this object? Gravity. So downwards arrow that represents gravity. And although there is another force acting on it, the other force is the pivot point, and that doesn't cause a torque. So this is the only force that's causing a torque. So if I want to work out my torque, I'm going to start by saying that R, which is the distance from the pivot point to the center of mass, that's where the force is applied, that's going to be x, center of mass. Next, I'm going to have to put the force in, that's mg. Now, if we have displaced this an angle theta, then by corresponding angles, this too must be theta. Why'd you do that? You don't remember corresponding angles? Okay. You had a traumatic experience in geometry honors? Okay, so here we go. I'm going to write this as a sine theta. Before I go any further, let's deal with the fact of whether this is a restoring force or not. I have displaced the object in a clockwise direction. Can we agree that the force is trying to push it back in a counterclockwise direction? Right, because I've picked it up to this side. Picked it up this way, which is clockwise. But this torque is trying to push it back this way, which is counterclockwise. So my torque is in the opposite direction of my displacement. So that gives me my negative sign. You just have to think about it. Usually you can just decide whether you want to make it positive or negative based on what's happening. Is it trying to push the object back to equilibrium? If so, that negative sign exists. And this equals I alpha. All right, we've done our force equation. Now our job is simple. Solve for our acceleration. So I'm going to divide both sides by I. That's it. So alpha equals negative times xcm mg sine theta all over I. I'm going to do it like you guys would do it. Nice and easy. I just put everything up above the I and not really care what it means, but it's not what I want you to do. I want you to tease out all the things that are constant, put them together, and then anything that's changing, put it off to the side. So does the distance from the pivot point to the center of mass change while it's oscillating back and forth? No. Does m change while it's oscillating back and forth? Does g change while it's oscillating back and forth? Does theta change while it's oscillating back and forth? Okay, that one's in. Does I change while it's oscillating back and forth? The moment of inertia changes while it's oscillating? I don't think so. It's going to be something like ml squared or mr squared or 1/2 mr squared, whatever our shape is, right? So I think we can rewrite this with a negative sign, a set of constants, does this fit? Do I have an acceleration equal to a negative sign, constants, and a displacement? Kinda. It's not a displacement, it's the sign of the displacement. So I'm going to write off to the side. Small angles. So don't pull it very much upwards, right? Small angles. Wave my hand, small angles, and bye-bye sign. It's just theta. Yeah. Small angle theorem. We can do that. It's okay. All right. That's it. That's what controls the motion. So now that we've done all this work, let's recognize that omega, why did it do that? Omega is going to equal the square root of x cm mg over I. That is omega for a physical pendulum. No big deal. Just a couple things. Remember, the period is 2 pi divided by omega. So 2 pi times square root of I over xcm mg. If you want frequency, you could have done frequency. We just tend to do period. So here's what I want you to do. Let's test this. Yesterday we tested this, right? We tested it for a grandfather clock, and we tested it for a wall clock. Do you remember? To try and kind of get an idea. Is this true? Does this work? I want to do the same thing. Let's pick a physical pendulum. I have one already set up, so I'm going to use a meter stick. A meter stick is a nice, simple physical pendulum. So let's just do it all right here. I'm going to take a meter stick, and we're going to oscillate it about one end. So our meter stick. Our meter stick has a mass of, they're like 80 grams, right? So 0.08 kilograms. What's the length of a meter stick? 1. Way to go. Good job. Now, we need more than this. We're going to need X center of mass. So if I'm hanging the meter stick, say, by an end, where's the center of mass of a meter stick? It's middle. Yeah, center of mass here at the 50 centimeter mark. Moment of inertia of a meter stick. What's that? That's it. Excellent, excellent. You deserve a prize. 1/3 ml squared. You need the homework. You need those points. All right, so I want you to determine the period. I've given you all that you need to do. Try it out. Find the period. In a minute, we'll measure it and see if it works out. And if you get it right the first time, this is it for today. You can work on your homework for the remainder of class. If you get it wrong, I'm going to find something else to do this with so that we can keep practicing. So a lot of pressure. A lot of